Hello everyone, today we will be talking about relative motion analysis. So we talked about relative motion in previous chapters for particle, but here we are going to talk about relative motion of rigid body. The difference between particle and rigid body is that we can have relative motion within one object. So from one point of an object to another point, we can have a relative motion. We talked about different types of motions for rigid body. The first one was translation. When all parts of the objects have the same displacement. So if we have, this is a rigid body, is translating to its new location. Let's call these A and B. Here the same A and B. If this is our center, this would be RA and RA for the second position. Then we have a displacement vector, we call it DRA. And we can write the same thing for point B in our rigid body. So when it's translation, DRA, our displacement vector for A is the same as displacement vector for B. And therefore the velocity at A is the same as the velocity at B. And that is true for any other point on our rigid body. The velocities are going to be the same. The second type of motion that we talked about was rotation. So if we have our rigid body here, and this one is rotating about a fixed point. So here our fixed point is A. And then we are going to have an angle, theta, and then therefore omega, and then alpha. In this case, there is no displacement for A, therefore no velocity for A. We have drB and therefore velocity B. You can find a velocity B by knowing the angular velocity, so omega, cross the radius RBA. And that's how we find rotation. In a general case that we have both rotation and translation, we call it general motion. You can think of as a rigid body is moving here and also rotating. In that case, the velocity of point B is not the same as the velocity of point A. We can break this general motion into two simple motions that we earlier talked. So we can say that that is true that VA is not the same as VB simply because the displacement is not true, not the same. But we can break it into the translation and rotation. So in translation, we say VB is equal to VA. And in rotation, we say that VB is omega cross RBA. So here in a general motion, the velocity of point B is velocity of point A plus an additional rotation that we have to consider that. This component, we call it the relative velocity of point VB with respect to A. So this one is referred to as VBA. The relative velocity. Again, when we are talking about a rigid body, we have relative velocity within one object from one point on our object to another point. You need to remember that this is a cross product VBA as a cross product formulation, which means that the order is important. And also VBA is perpendicular to both omega as well as RBA. So this relative velocity formulation is very helpful for us, and we use it for solving different problems. For example, when you have a disk that is moving in this direction with an angular velocity of omega, if you want to find a velocity at point O, you can find a velocity about this point. We call this point of contact C. So if you want to find VO, it would be VC plus the relative velocity of VO with respect to C. What is the velocity at the point of contact? What is VC? VC is 0. If we have rolling, if there is no relative velocity between the ground and our disk, then at the point of contact, the velocity is 0. And to write the relative velocity, we know the relative velocity is the rotation. If we are interested in the velocity of one point in the object with respect to another point, that would be ROC. So this is a vector formulation, and you need to remember that in vector formulation, we have an I component and J component in 2D, which means that technically we have two equations and we can solve for two unknowns. So whenever a problem involves relative velocity of a rigid body, you need to remember that you can solve for two unknowns. The other important thing is that when you're talking about the relative position vector, let's call this B and A, or B with respect to A, that's our relative position vector, is not the same as the position vector RBA. That's the position vector, that's the relative position vector. So RBA is actually from A to B. So this is our RBA. In contrast, RBA would be from B to A. So in relative velocity of rigid body, we are talking about the relative position vector. So you need to remember the difference between the two. Now let's go and solve a problem here. That's problem 12 of chapter 16. That's part of the fundamental problems. So end A of the link had a velocity of VA 3 meters per second. So we have the velocity of this point. Determine the velocity of the peg at B at this instant. You're going to find the velocity of B. The peg is considered to move along slot. So we don't know the magnitude of velocity at B, but we know its direction. And we have the velocity at A. So we can write our relative velocity formulation to find the velocity at B. We know velocity at B is the same as the velocity of A. The other point on the same object, we are analyzing this rod AB, plus VB with respect to A. I can rewrite this equation to include the rotation component. So VBA would be omega cross RBA. So let's look at our equation to see what we have and what we don't have. The problem is asking for VB. So VB is a vector here, but we have the direction. We don't have the magnitude, but we have the direction. VA, we have everything about it. We have the magnitude and the direction. So far we don't know the magnitude of VB is not known. Then we come to omega, which is omega AB, the angular velocity. We don't have omega. RBA, we have the dimension and we have the direction. So we have everything about RBA. So we have two unknowns, so we can solve the problem. Our first task is to present everything in a vector form. VB, let's present it in a vector form. We know the direction. Let me draw my coordinate system so we know what we are considering positive and negative, XY. I will write VB here, VB. I don't know the magnitude, but I know the I component and J component. The I component would be negative and J component would be positive. VB will be moving along that direction. When A is coming down, B would move into to negative X and positive Y. So the X component would be negative, negative VB cosine 30 I plus VB sine 30 J. So I wrote my vector VB in a vector format, in Cartesian format. VA is the second vector. For VA, the problem is telling us that the velocity is 3 meters per second and the direction is negative J direction. Now we have omega. So if this one is going down, let me clean up the image a little bit. Omega would be clockwise for us, and clockwise would be negative. That's our sign convention. So the other vector that we want to find it would be omega. We don't know the magnitude, but I know the direction would be in the direction of k, omega k. So omega, when it is clockwise, is towards negative z, and when it is counterclockwise, is towards positive z. To find the direction of omega, your forefinger should be in the direction of rotation, and your thumb would indicate the axis. So here, if you're using your right hand and you're turning your four fingers in the direction of rotation, you would see that your thumb would indicate a direction inside the page, which means that negative z. That's why clockwise is negative and counterclockwise is the opposite. And you have to remember, we are using a right hand rule, so you have to use your right hand. If our motion was counterclockwise, let's say this motion, and now if you're using your right hand and four fingers in the direction of rotation, your thumb would be coming out of the page, so positive z. So here we are dealing with negative z or k. So we found VB, VA, omega. The other vector is RBA. And RBA is from A to B. So RBA. And we have the angle here. So, and we have the magnitude, which is 2. So 2, both X and Y component would be negative. So if I write RBA here, would be negative. 2 is the length and the angle cosine 45. Because cosine 45 and sine 45 are the same thing, so I use cosine for both of them. I plus j, both components have the same magnitude. So I found everything in terms of Cartesian components. Now I can just put my vector together and find for the unknowns. So here I write my vectors again. So VB is VA plus VB with respect to A, or omega cross RBA. We are talking about cross product. So the direction is important. VB, we found the value for VB. We broke it down into its Cartesian component. So VB is negative VB cosine 30 I plus VB sine 30 J equals VA was negative 3J. Omega, we don't know the magnitude, but we know the direction, was negative omega K. Cross our vector R is negative square root of 2I, negative square root of 2J. So if we go to our BA, negative 2 cosine 45 would be a square root of 2 over 2. So that would be negative square root of 2I, negative square root of 2J. So in this equation, when we look at the whole equation, we can see we have two unknowns. One is omega, and the other one is VB. But we are writing a vector formulation. That means that we have two equations, one for I and one for J. So for I component, I have this. The I component on the left side should be the same as the I component on the right side. So on the left side, I write negative VB cosine 30 or a square root of 3 over 2 equals, on the other side, negative, this is the J component, I'm looking for I component. If I go here, I know K cross I will give me J, but K cross J will give me I. And K cross J, the cross product will produce a negative component. And here, so negative, and the other two negative would go away. I have a negative here and negative over there, so that would be negative 2 omega. So that's for the I component. For the J component, I'll write it here. I have VB sine 30, so half of 0.5 VB. Sine 30 would be half, so 0.5 VB. I have a J component over there. Also, the cross product of K times I will give me a J component. The cross product is not going to create a negative sign, so it's just a sign that we have here. K cross I would be J, have negative, negative over there, so positive. So it would be positive times positive plus positive square root of 2 omega. So from these two, I have two equations and two unknown. I can find omega to be 5 radian per second. Then I have VB to be 8.33 meter per second. So going back to the problem and looking at the problem, you can see the main thing is to know that A and B are on one object. So we can write the relative velocity of rigid body equation. VB is equal to VA plus VB with respect to A. What is VB with respect to A is the rotation, omega cross RBA. In that equation, for VB, we don't have the magnitude, but we have the direction. For here, for omega, again, we don't have the magnitude, but we know it's in the Z direction. If we assume a wrong direction for VB, at the end, we are going to find a negative value. So the equation is going to correct itself. The other important thing is about the direction of omega. We said counterclockwise would be positive, clockwise would be negative, and the reason is the positive z, negative z direction. If you write everything in terms of its Cartesian components, then using the vector formulation, if the two sides of the equation has to be the same, then the i's and the j's have to be the same. So I write the I component for the left side and the I component for the right side. Similarly, the I component for the j component for the left side and the j component for the right side. And you need to remember for cross product, I use this. You can use the general cross product equation, but I use I, j, k, and this is positive. So whenever we are talking about j cross k would be positive, it's in the direction of positive. So the cross product itself is not going to create any negative sign. And similarly here, when we do k cross I is positive, so the cross product itself is not going to create any negative component.